would probably explain why it's taking so long, because Schecter's got a lot of personal stuff going on.
Yeah, I don't think our grades are gonna come out well.
It was a very long test.
I don't think
It
it'll
was
come out
pretty
well.
difficult.
It will not come out well. The average is gonna be a 60, 70.
No, I did better than that. Yeah, I think I did better.
I knew what I was doing, but I just didn't have a whole lot of time. I was just like, the whole test. Like, it was,
Yeah, like
how many
you-
pages? Like 16 or something? 12? Yeah.
12.
But, yeah, I studied really hard for that. And I think I did better than I hope I did better than a 60 or 70. If I did, I might go mad, you know.
I got to that
You don't know
one.
what they're gonna be picky on, what he's gonna be picky on.
What got me was labeling the very last page.
Oh, that was, yeah, I didn't
I
have
was looking at it, I was
time.
like, can't salt, gypsum and anhydride like all be the same thing?
Yeah. The only thing I know is anhydride has the, what is it, high density, and then salt has low lower density, and I don't know about gypsum.
For that one, I was like, okay, cell layer, cell layer, cell layer.
Yeah, it was mostly shale.
Yeah, all those forms were shell.
Yeah,
That's what I got.
then at the very end it was like salt or anhydride or something, and
If
then
I
I
had a couple
just
stragglers, I would just put in like what I didn't have.
Yeah. I really, at the end, I pretty much didn't have any time left, so it was just kind of like shale.
Fill in whatever you could.
Yeah.
Yeah, that's all like, I was just looking forward to having this entire week to devote to reservoir, and bleeding would be over for 663.
I thought at work you were to do one or two more classes.
Not 8.
And make it work like 7 to 9 o'clock at night. Couldn't you do like 3 to 5? 4 to 6, something normal?
I mean, I'm assuming he's got meetings or something.
Yeah.
That'd be my guess, at least.
What's with the short meeting on Thursday, you know, during the day? I didn't understand what you were
Then
talking
we have
about.
one in the evening.
Yeah,
We
there's
have
one
an hour at this time on Thursday, right?
Yeah, during the day, and
7 to 9.
then at night, I can't make the night one, but I hope he doesn't go with it. Well, I can always watch it online.
I was thinking that maybe someone has a test at that time in this classroom, but I don't know if it was referenced to our test or someone else's test.
Yeah, I don't know. I didn't understand the email. Oh my god, someone just rolled over. This is worse than 663, or, sorry,
That's what
665.
I thought it was too, but students.
That's during 1 o'clock. That's all I have to know the next lecture, and we'll on next lecture.
So this is for all you people who finished the test. I'm gonna tell you how you did it, so you feel bad because you missed it. I'm doing it this weekend. There's a final.
Wait, we have a class after.
That's what we don't know. We don't know if the test.
No, I'm not
Wait,
showing up.
what?
You guys the Thursday how he said the first class ends early because of a test?
We don't know if that's our test or.
I don't know what he said.
I think he meant that there was another test in this room, so we can't use.
We have our reservoir final on Tuesday.
Have fun with that.
Thank you. Appreciate it.
Well, I hope it's gonna be better than ours.
Yeah.
That was fun, wasn't it?
With King, the last part.
King
Y'all have a King
was
one?
an ass race.
Ugh.
King was an ass race.
Well, he gave us like basically just like a slight derivation of the diffusivity equation, and didn't give us any of the needed equations. And yeah, I was
so
screwed.
glad I dropped that class.
Yeah, it was a good.
You were there?
I was a distance learning student on that one.
Why did you drop it? Barrow said it wasn't that bad.
Oh, I hated that. I'm not talking about it.
Yeah, we're being
It
recorded.
was good.
I did not enjoy that aspect of the class.
That was a good call.
And I was working and taking 661 too. Not that 661s are, but just the two with mowers scheduled at times. Investing, what was it, like 25 hours a week on their homeworks? That was just.
Okay, yeah,
that was
perfect homework, but as
ridiculous.
long as you don't know chemistry. If you didn't know chemistry, her homework for,
Yeah, 'cause she's a chemist.
Yeah.
I'm not a chemist.
hello, Professor Tab. What's going on? Like, there's like a bunch of cool people.
Oh, that's somebody's got a conference here.
Water.
There's a bunch of old people, then there's a bunch of young people who don't know what they're doing, walking around.
Are you implying in this room, or just where you see it? That's pretty good, huh?
No. Yes, no.
Christian, why were you, on campus at 7:30 this morning? None of my business, I just figured it out.
What? Oh,
Were you sleeping in your office again?
well, sometimes I do that, but, I was getting in early.
Sorry?
I was getting in early because I have a presentation to work on.
Really? That seems a little far-fetched. Okay, so who's got a moment of awakening for us?
He does.
No. The Venezuelan gets a free ride today. He suffered in ways you can only imagine. Or maybe not. Dennis, we miss you.
No, we don't.
You can believe me. All right, so where we left off last night was a lot of discussion about Fetkovich. I think we're pretty good. We were further down the list.
No, the
You didn't make it clear.
Who wants a spring up? I guess the ladies do. What do you want to say? Sorry, you were speaking.
You didn't make it clear what his thing was used for, because it didn't seem like it would be that useful in determining reservoir properties and the volume seems to be like you can't really match.
The volume you can, but the other properties you cannot. But we'll look at that some more today. Maybe not as in detail as you wish, but hopefully, be right back. The worst glasses, man. You can think about touching them and they get smudged. With rubbing them sandpaper. Okay. So we talked a little bit last night about what happens when B is greater than 1. And what's the answer? So if we were to write a big note on here, B is greater than 1 only for transient flow. Correct? For the sake of argument?
When it's less than 1, it's only steady state and steady state.
It implies that it's due to steady state. There is no such thing as steady state. That doesn't mean anything.
That's fine.
How can you have steady state?
Molecule by molecule equation.
Can we have that?
No.
So we need to stop saying steady state. Not you need to stop saying it, we all need to stop saying it. It just does not exist. Okay, so voting for transient flow. What does that mean? What also happens to these equations? What do they extrapolate to? Okay, so let's take all this off. What happens to this equation for t equal to infinity, or I say t approaching infinity? And 1?
N equals to QI over D.
NP max
Yeah,
equals QI
over D by.
over DI. Okay, what happens to the next one? NP max is equal to QI
1 over D.
over 1 minus B DI. This is only for B less than 1. How do we know this? M2. What happens when t approaches infinity here? Anything multiplied by infinity is? Anything infinity multiplied by something plus something is? The logarithm of infinity is? So what happens? This one, NP max, goes to infinity. Or t approaching infinity, b greater than or equal to 1. Okay? Now we can stop it. We can choose a time to stop. Okay? Infinity is a long time, right? So even a small number times a large time is still going to be a huge number. So this one, you're oriented on that. So if I were to ask you true-false type questions and say the exponential decline has a non-infinite extrapolation, the hyperbolic decline for b greater than or equal to 1 extrapolates to infinity, if not constrained. Those are all reasonable questions. So how do we use a b greater than 1? Where does that occur? No, but where does it occur?
On the left, the curve.
Right, but, sorry. Good logic. Do fractured wells have regimes where you would have a b greater than 1? Okay, so let's say that we substitute in this equation b equals 2. Right? What's going to happen in this equation? It's going to be QI. Ultimately, what's going to happen? Alpha square root t.
Mm-hmm.
Is that right?
Yeah.
Everybody okay with that? That long time. That's 2. Anybody who can't read my handwriting? And so that is t raised to the square root yields a half slope on a logarithmic scale. So if we see something that is declining at a half slope, that's a b of 2. Okay. Will that happen? Sure. All the time. High conductivity vertical fractures yield a half slope. Low conductivity vertical fractures yield a quarter slope. A quarter slope means b is equal to 4. What do we say to that? In the words of our Venezuelan friends, mate de Dios. You will not make a production extrapolation with a b of 4. You will go to the devil if you do something like that. Even a b equal to 2 is a bad idea, because you know that's what's going to happen if we're looking at a logarithmic grid, is we may have some b equals 2 behavior, but then it's going to tail off like that. So if we make an extrapolation with b equals 2, all this extra area is wrong. okay? Now, this is an introductory survey course. These are kind of weird concepts, everything else. I'm certainly not gonna try to trick you or anything like this. But I deal with this every day. And when I was teaching this course 5 years ago, I would have said, you will go straight to the devil if you use B factors greater than 1, blah, blah, blah. But there's a unique situation. If the permeability is low enough, and you have fractures, hydraulic fractures, you're gonna be over here for a very, very long time. It could be 10 to 30 years. Just off the top of your head, does anyone want to know why this happened? This red part? What happens is you have all these fractures, and then you have this pseudo boundary around it, which is called the SRB, the stimulated residual volume. We already talked about all that, right? What else can cause this red line? This is a problem for your generation. Mine's too old. What else can cause this behavior?
You hit the boundary?
Tip effect?
Sorry?
Tip effect?
It's not reservoir related exactly. Good thinking. What happens if I slowly add weight onto you? You gonna be able to climb the stairs at the same rate? And the higher you go, the more weight I add? It's kind of like what happens when you get old, right?
What does the weight come from then?
Well, that's a really good point. Let's think about it. We have a mile-long horizontal well, and then a 2.5 mile long vertical portion. And those fluids have to move all the way up there. Now, who's against them moving up there? Mr. Friction, Mr. Gravity, Mr. Segregation. Is anybody else part of this? So what happens is once you start having a back pressure on the formation due to the liquid load, it's not going to remove itself, is it? Now, the way it's generally dealt with is with plunger lift, because plunger lift is next to jet pumps, is the easiest to use because it doesn't have any really moving parts or anything. A plunger looks like a giant dart or projectile. It drops down into the wellbore, through the tubing, passes down, and then when the pressure builds up to a certain point at the bottom, pushes it out. There's all sorts of variations of this thing. There's smart plungers, there's pass-through plungers, there's this, there's that. Sometimes you can't even see the plunger moving because it's passing, the fluid's passing through it. Other times, it looks like the pressure just shoots up when this thing comes up because it's pushing the fluid load up. Okay. So where I'm really going with this is this false positive or this false boundary could be an effect of liquid load, something that's happening in the wellbore. The single biggest challenge right now in unconventional personal belief is going to be field operations, liquid loading, liquid management. And nobody thought of it. Because they just figured, what the hell, they're overpressured, they'll produce, everything will be fine. And for some, that's been true. For the gas plays, for the Haynesville, for the Marcellus, it hasn't been a problem. But for all the liquid plays, imagine that you've got pneumonia, and instead of getting better, you just keep getting worse and worse. What's going to happen? You're going to die. And that's what's going to happen here. If they don't get the liquids off, they'll eventually put themselves down. Now, this happened in tight gas as well. But the difference was we were dealing with a single vertical borehole with a single fracture. We're now dealing with 30, 40 fracture stages and 1.5 miles, 2 miles long horizontal. A lot different. Yes, sir.
Can you explain in graphic what the loading is? I didn't get to.
You will bore.
I'll draw it out here, I know we need to move on, but he's right. For everybody else who's out there, let's talk about it. Okay, so Sam wants us to draw a vertical well, right?
Doesn't matter. You can
Well, let's
have
do
it
the vertical well first, so that'll be the easiest. Okay, so we've got tubing, let's make this easy. And this is packed off, that's what these X's mean. And usually have a valve here. Okay, so you've got some sort of fluid coming out of here, oil, gas, and water. Okay? And down here, we have perforations which allow flow into the well. All right, you ready? Okay, so first, our enemy is Mr. Water. Okay, Mr. Water sits down here and he rises up. Does the composition of the water ever change? Not really. Does the density of the water ever change? Not really. Does the amount of production of water ever change? Yeah, it drops down. At first, the entire column is water. And generally speaking, these things are overpressured, so it pushes the water off. So we have a curve over here. And first curve will be water. And it's huge. And it drops off fairly rapidly. I may have drawn it dropping off too rapidly, but you know, there's a little bit of buzz around it. There'll be some noise in it.
Is this at the beginning of the life of the well?
Yes, this will be,
So you're
I'll
probably
go ahead and
like
put the-
drilling fluids and all that?
no, you never want to do that. You know, you'll flush it out with a completion fluid before you,
So that's the, is that the water you're talking about?
the water would
All
be the
the-
fraction of fluid. Okay, so let's say, and I didn't draw this to 0 time, but, let's say this is, for lack of a better point, that's 0. This would probably be about 1 month. Okay? So, roughly speaking, you know, you may recover 50, I won't say it that way, because that would confuse you. You will recover the majority of the fluid in 1 month. This is not going to go on forever. But the area under the curve for water, it may only be 20% of what you injected. Okay? Does everybody understand that? So whatever we used in stimulation, 80% of it, 70% of it stays there. There are a few occasions where you have water-producing shales and you just continue to get water from the formation, but those are pretty rare. And frankly, they're not desired. Okay, so there's the water curve. And then what happens typically is gas comes on board and it'll rise up and it'll come down like that. And you can imagine the gas will first bubble through and then it'll flow through like that. Depending on the play, then you have oil coming in, and oil and gas are quite often coincident, and then they look like that, and it'll come in like this. Now, all this time, what's happening is pressure. So over here, we'll draw an axis for pressure. And this will be pressure down here at PWF. We're not gonna bother with surface pressure for the moment. PWF. What's gonna happen is it'll start high, and it'll come down, 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 down. Sometimes pressure has a little bit of a bump when these come in, because gas expansion provides some energy, so maybe it'll change the slope of this, it'll change the influence of this a little bit. Okay, now, what happens is when you start getting down into, say, a zone of, let's throw a number out, 6 months. Your pressure may be too low to lift. And so what happens is this column will start exerting back pressure on the formation, and it can't lift anymore. That's what we're talking about. What are the solutions?
Unload it.
What are the solutions? You can put gas lift in with little mandrels, and you can inject gas down the back side. How much maintenance is required for gas lift?
Need a compressor,
And that lightens the column, right? How much maintenance is required? Practically none. Okay, that's why it's preferred. Maybe changing the manuals, maybe redesigning them, that sort of thing. These are the manuals. Little black toggle things that are drawn. You guys didn't cover this in production class? You know, do it there. Sorry?
it's not offered.
Oh. So, you could have gas lift, what else could you have? Our favorite thing in the oil field is pumps.
Yeah, you can pump
ESP,
Okay. An ESP would be too high a volume, most likely. Do you use ESPs in Venezuela?
Not that much.
Sure you do.
Fuel well.
For wells that are producing a lot of sand or a lot of water, and you want to move a lot of volume, you can. But we use rod pumps mostly. Why rod pumps? They have 2 moving parts. What's the moving part? 2 ball bearings. Ball bearings are called a standing valve and a traveling valve. When you pull up, the standing valve seats, and you pull on the upstroke it pulls the column up, and on the downstroke it produces through it. So it's a double acting pump in that sense. Rod pumps are great, but they have low volume, only a few hundred barrels a day. Also, do rods like to be in curves? No. Why? Because then the rods will rub against the tubing, and one of the two is going to give. No matter how many spacers or cushions you put in, sooner or later, I mean, you guys do understand these wells are not straight. And the rods are gonna hit the tubing probably 500 times on the well way down. They're just like that. It's not unusual to have a rod part or wear a hole in the tubing, etc. So we got pumps, we got rod pumps, we got jet pumps where you inject the fluid down the backside. You got gas lift, you got plunger lift. Plunger lift, let me go ahead and answer this, and I'll come back to you. Plunger lift is a device that sits up here, and it's got some cups on it, and it drops down, and it seats here, there's a seating nipple, and it waits until the pressure builds up, and then it pushes the fluid load up, like that. It's a very clever device. And there's all sorts of smart ones now. There's a flow-through device. There's a device that has a pressure gauge in it. There's clever stuff. Okay. That's about it for the simple stuff. Yes.
What about well cycling? There's that,
Cycling,
yeah, like,
puff and puff, you mean let it build up?
yeah.
That's a 4-boy approach, but a lot of people do it. I've known a lot of guys that'll shut the well in for 3 or 4 days, produce it for a couple of hours, shut it in for 3 or 4 days, produce it for a couple of hours. So you imagine that having a rod pump on it, like the one we have out here, and letting it come on for 2 hours a day is going to make you a hell of a lot more money than somebody going out there and flushing the tubing out every 3 or 4 days.
Well, like, something we will do is, we'll shut it down for maybe an hour, in increments, and let it fill up, and then it just pops back
But
on.
somebody's gotta do this manually.
We have a computer system that can do it.
Okay. Automatic choke or actuated choke, some sort of, what kind of well is it?
It's conventional one.
Is it gas well or?
Oil.
How much gas, what's the GOR?
Oh, I don't even know the GOR.
What I'm trying to do is get an idea for what's pushing it. It's probably the gas cushion.
Not a lot of gas, I know that.
It's probably the gas cushion that's pushing it. Okay, so let's pretend now, for the sake of time, that we turn this well and we have a curved portion. And that curved portion is huge. It's on the order of the same length. And I'm drawing this, I'm going to use the instructor's prerogative here. It's kind of cool how the old part didn't erase. And I'm going to turn it. What's different? Nothing. Except now, the whole length of this well might have water sitting in it, and oil sitting on top of that. Oil is green. And then gas sitting on top of that. What will gas do? It'll race through and leave the others behind. Does the well really look like this? No. What does it look like?
Crazy curve. It won't be that straight.
That looks like a stomach or a snake or an intestine. Sorry about that. But you get the message. So your liquid will sit on the bottom here. We don't really know what this looks like. We use production logs to try to figure it out, but we're still not sure. How are you going to get the liquids out?
You lower the surface pressure.
The only thing you can do is pump it off. Nobody's going to drop below this point because they're going to get the equipment stuck. Okay. That's their biggest fear. Anybody got any ideas?
Well, CO2 injection.
Where?
At the end of the well.
How?
Drill another well.
How much does it cost to drill a well?
Depends.
Depends.
Can we quote Austin Powers,
OBD.
Dr. Evil? Millions of dollars. That's been proposed. To use old wells, old vertical wells nearby, crack the living daylights out of them, and push gas through them. Is the gas going to go where you want? It's going to go where it wants to go. And yes, it should go to the path of least resistance. But what if it skips and, half the borehole and goes here instead? And it could. I mean, there's some crazy stuff out there. Someday I'll tell you a story about a project I was on where the general manager insisted on injecting CO2 in a pattern, and 3 patterns away was somebody else's lead. It skipped 3 patterns away and showed up in somebody else's lead the same day. You can only imagine the vultures, i.e. lawyers, that showed up shortly after that. These guys thought that they had picked an isolated area where they could test it. And the ironic thing is, I don't usually quote SB papers, but there was an SB paper on this topic It told, you know, another company's experience, and exactly the same thing happened. And everybody thinks they know their reservoir very well. But in that SB paper, they said they injected CO2, expecting some sort of a response 6 months later, and it happened 6 hours later in a pattern, you know, removed from where they were, and everybody was like, what the hell happened? Well, you know, there's fractures all over the place. There's subseismic faults, there's all sorts of things. My point is, I wouldn't inject something down there. I know we're getting off topic. I heard somebody suggest a snorkel.
What?
Come down here, and something, and bubble gas through it.
Gas lifts, like we did.
It'd be gas lift the hard way. I think it's a brilliant idea. I think somebody in this room ought to go out and raise some money and try it.
But not you.
I'm destined to be poor. I have taken a vow of poverty and misery the last part pertaining to you. Sorry.
How are you supposed to control the
That's the first
path?
question somebody asked. What's the second question somebody asked?
How much is it cost?
How much more?
What if we get stuck?
Well, gas lift is, when you do it, it's safe.
No. What if you get stuck with your snorkel?
Because you use coil tubing to get it down there?
Yeah, but what if you get stuck?
Well, then that's the problem, that happens all the time. I mean, coil tubing is used all the time.
Yeah, but then you gotta pull the whole thing out,
Yeah.
joint by joint. You lose it all. I mean, I agree that you could probably design it to where it wouldn't happen. But I think it's a brilliant idea. I'd love to see at least a pilot of something like this. You know, maybe even using tubing inside tubing or something like that. That might be something to try. I don't know. I know we gotta come up with something. The next 50 years of unconventional is gonna depend on our ability to unload wells. You heard it here first. All right, we gotta get back to compliance analysis before the rest of the group wants to kill me. Although they do anyway. Okay. So, suffice it to say, these are our working equations. Nobody's asked me, and I'll ask you, let's do a sniff. You can never find the sniff thing when you want it. Isn't that pinned to the...
Yeah, but that's somebody else's profile.
No, this is me. I logged in at 7 o'clock this morning to make sure we do it. You guys see this?
Yeah, right there.
All right, this will be an opportunity for someone to shine. You ready, Jeff?
What?
It's your opportunity.
How do you make that stick?
I don't know. I think it's because I did it in something else. All right. I want to marry these two. I want a hyperbolic plus exponential. Dennis, how do I do it?
Add a weighting function to it, or that?
Okay, so he says that y will be equal to y hyperbolic times alpha p plus y exponential 1 minus alpha p, where alpha p is the weighting function.
Yeah.
Clever boy, I like it. What's alpha p?
Geo?
No, I mean, you just made it up. It's GOK, right? Is GOK a word in Thai? No, just making sure. You know what I mean? God only knows. What's it equal to then? Make me happy.
It'd be a function of B.
Well, we don't know. That's the point. So absent that, what's another approach? What else? The drillers are all going, please get away from this. All right. Anybody else?
Well, you did describe last time that the software package that we used had almost if else statement within it.
Correct. And how does it work?
Um,
It's amazing that you can remember that. You can't remember what day it is.
August 6th.
Are you sure?
Yeah.
Okay, so what Jeffrey wants to do, he wants to say the Q, T, so what's your favorite color, Jeffrey?
Red.
Good. So here's the hyperbolic portion. And by the way, this is logarithm. You, sorry about that. Dennis, what's your favorite color?
Green.
I need that. Okay, so now, we're going to somehow splice Dennis's green curve, green on. Okay? So this is the exponential. And this is the hyperbolic. How do we splice it together?
Well, you need a D of the 1 over T, dt or dt.
How would you splice it? Anybody?
Equal value T,
Sorry?
find the T value where the function is equal.
Okay, do you want rate? This is an interesting question. Let's ask the mathematician. Do we want rate to be equal, or do we want the derivative to be equal? Okay. Without details, it'll be the slope, not the rate. Okay. So what we have to do is we have to investigate from this equation where does the d of t, the calculated decline rate, where does this suddenly equal our di exponential, which would be from this equation. And we can do that with an if statement, like Jeffrey was saying. So we just walk down the red curve, we go ahead and calculate the red curve, and then we just find the point where that equals that, and then we use that as our trajectory for the rest of the curve. This is standard practice. It's like the American engineering system versus the metric system. You may not like it, but that's that. We're going to work with this. Now, I'm not saying this is reservoir engineering, but I am saying there's a lot of reservoir engineers who this is all they do all day long. Is there a better way? Yeah. It's, again, beyond the scope of this, but a better way would be to use diagnostics and determine where that occurs. Most of the time, this occurs beyond the data. You have data here, and then the splice occurs out there. Dennis isn't liking this at all, because then you have no way to calibrate this. So how do you pick this value? You pull it out of the air. Is it acceptable to have a low value or a high value? Obviously, a high value means what? A higher value would be that you would see this sooner. So it might be back here.
You get more.
And then a low value would be, I need to extend the hyperbolic. A low value would mean that we would meet up with it way out here. Come on. So there is some practice to this. So this would be DI, EXP low. This would be DI, EXP high. Dennis, who invented reservoir engineering? The IRS. Well, probably wasn't right to say who invented it, but who was a cause. Okay. Who's going to invent this? Who's going to invent where we come with our extrapolation? Who's more scary than the IRS? Yeah, the SEC. So best practice will be some sort of intermediate value that everybody agrees on. Generally speaking, it's thought to be about 10% per year. But if you come along and say, well, my well is better and it's 5% a year, you can imagine you're going to get a lot more reserves than the guy who used 10. So you better have a real good case as to why. Now, I know you're going, geez, people make money with this. They're the guys with the suits, the ties. There's a best practice for this, and people adhere to it. There are issues with this approach. But like I explained about deliverability testing, as long as everybody plays with the same rules, it'll work. This is probably the single most common technique for estimating reserves. There's absolutely nothing wrong with it. Okay? In the hands of someone who is conscientious. Can you automate it? No, because if you automate it, what happens then? You don't know the location of the point. Can you specify and automate it? Yeah, sure, there can be an auto fit on the blue data points, and then you can come off of that with your decline. But do you want an auto fit to govern your reserves? No. Remember what I told you when we started talking about decline curve analysis. What's the first thing your mother told you? Never extrapolate anything but a straight line. So that's where this came from. Because people want to be comfortable with what they're doing. All of the naysayers on shales have basically disappeared. They were all saying we're using too big a p-value, we're doing this, we're doing that. You don't see many articles on that anymore. Why? Because there's something like 40,000 shale wells in the U.S. right now. And within a reasonable category of prediction, people have done pretty well in year-to-year type predictions. Are you really interested in reserves? As a benchmark, yeah, but you're a lot more interested in production, aren't you? Production affects everything today. If you make a mistake in reserves, nobody's going to get canned today, but if you make a mistake in production, and 6 months from now you're producing substantially less than you said you would, something's going to happen. What happens if you're producing more than you said you would?
Nothing.
They're gonna wonder why you didn't figure that out too. More or less is not good. Being right is good. This is why every year, every company updates all of their projections on a year-to-year basis. And the objective is simply to be aware, in my opinion, of what you're gonna produce. Okay. Any other questions about that? Does it matter what the B value is here? No, not really. I don't want you to go higher than 2 for shale wells, for horizontal multi-frac wells, but it's probably the case, 2, but not greater than 2. Greater than 2, you better have a really, really good reason. There are some shale wells that show 3 for a protracted period of time. My guess, where I could be wrong, is that it's naturally fractured. My guess. Which means the wells are producing better than we would expect. Okay, we already talked about these before a little bit. There is a reserved plot for the exponential case. There is a reserved plot for the harmonic case. There is something that can be rearranged into a straight line for every case in between. But then it becomes what? It's not an analysis plot, but a validation plot. You would have to make an estimate because you need that number to make that plot. So that means that you would have to determine these variables in another way. So you could perform an analysis where you make that estimate and then revise it. And that was how I presented this whenever I wrote the paper on this, is that you would go ahead and perform your analysis and then you would project this function as a validation function. It seems sort of abstract, but it would be a useful thing to do as a validation plot to make that, or as a validation function to make that function, plot. And of course, this is only valid for B less than 1. I'm not glossing over this, but I think we've covered it to the point where everybody understands what a straight line on a particular plot looks like. So if I were to give you a plot of rate versus cumulative production, or log rate versus cumulative production, you should be able to make an extrapolation.
When I have more paper.
I'll do the plot for you. They'll be the data will be plotted on the graph. But you'll have to know which part to make the extrapolation from. Does that make sense? Yeah? Yes? Are you scratching your head mentally, or? Okay. All right. So the derivation of the exponential decline is you take the oil material balance equation and the oil pseudo-steady state flow equation. Both of these, the oil material balance equation is actually a mass balance. It is rigorously correct for the assumptions that are stated. The oil pseudo-steady state flow equation can be derived. It is also rigorously correct for the assumptions that are stated, that is, it's a liquid. You differentiate both relationships, so you have a d, p bar, dt, you set those equal to each other, and when you do that, something has to break. What has to break? Well, you have to assume that the pressure is constant. I did a terrible thing on an exam a number of years ago. I gave this exact problem, and I did not tell them to assume the PWF was constant. I told them, in fact, the PWF was not constant. How would you solve this? Well, you would have to specify the derivative of PWF in order to solve this equation. If you assume it's constant, obviously the derivative is 0. So that was pretty fun to grade. I think 4 people out of 100 got even close. So don't worry, I'm not going to do that. Okay, maybe in 620, right? Equate results. This gives us the first order ordinary differential equation, which is linear, hence it can be separated, integrated, and then you exponentiate the result, and the result is that the rate is exponential. This has been known for a very, very long time. The very first time that I know it appeared in literature was a paper by Fetkovich et al. It was in the late 50s. It actually was for a multi-layer cave, and they were trying to demonstrate this concept. Okay? Prior to that, it was Arps. It was sort of empirical. Russell proved it in the early 60s as well. He had a relationship he was trying to be an advocate for. But the exponential decline is an analytic expression. So all of the theory, all of the hopes, all the dreams that you had, it works. But what are the assumptions? The operative word on this page is what, Sam, dude? All right? And oil means what? Constant.
Mu, CT, and B.
U, C, and B. Okay? That's what oil means. These properties do not change. What happens for a gas? Does the compressibility of the gas change with pressure?
Yes.
Are we in a room filled with a gas? The compressibility of that particular fluid allows my voice to be heard. What about the viscosity of a gas?
Okay.
The viscosity of a gas, you can run your hand through it, you can feel there's some resistance. At a higher pressure, there'll be more resistance. At a lower pressure, there'll be less resistance. It's clearly a function of pressure and temperature. Is this equation valid for gas? 3 options. Yes, no, or maybe.
No.
Maybe. What's the maybe? Yes.
At really high pressures, these things become...
Very good, Jeffrey.
It's
At
called...
very high pressures, small drawdown, there's very little change. Now, of course, it's totally impractical, but he hit the nail on the head. At high pressures, near the initial, there would be very little change in the properties, so the exponential decline would be expected. So if you're dealing with a very high pressure reservoir, low drawdown, you would expect to see something like an exponential.
Is it in the supercritical region in the phase?
It just has to do more with the fact that you're not having very much of a drawdown.
Oh.
So you're very close to the initial. Let's say that your production pressure is 99% of your initial pressure, then it's going to act like a liquid, all things being equal. But on the other hand, if you do what Fetkovich said and you make the bottom hole pressure 0, that's the most nonlinear case you can have, or the most, I shouldn't say nonlinear, but it will be the case where the properties are most variant, and clearly this condition doesn't apply. So in the case of a high drawdown, is it hyperbolic? It's an unfair question. It's not. It looks hyperbolic, it smells hyperbolic, it tastes hyperbolic. It's not hyperbolic. And this is where Fetkovich sort of waved his hand and said, it's okay, gas will always have a hyperbolic B factor of between 0.4 and 0.6. This is based on experience. And it looks like that particular guidance is quite apt. Okay? But the reality is it's not hyperbolic. It's not going to kill you to assume hyperbolic, but it's not hyperbolic. Okay, this is a case from Arps' paper, and in this case he fitted a system of oil production rate on the y-axis, which is logarithmic versus time, and you'll notice that I've drawn in both an exponential and a hyperbolic. Anybody want to find the missing link here, or the problem with this data set? This data set is a group of wells, not a single well. If you add exponentials together, what do you get, Neil? You don't get an exponential. Not unless all the coefficients are the same, right? If you have exp of minus 4, exp of 4t, exp of minus 2t, exp of minus 6t, you add all those together, that's not an exponential. But if you have EXP of minus 4T, EXP of minus 4T, EXP of minus 4T, you add all those together, no matter what their multipliers are, it's exponential. So, adding multiple wells together, an exponential would be a coincidence. If you add a series of exponentials together, Dennis, what do you think you'll get? Okay.
Considering that, let's say those wells are from the same reservoir, I mean, if they have
Good, good, I like where you're going.
CT plus, BO, would behave more like exponential.
In theory, you might be right. So what was that coefficient D a function of? It was a function of whatever this coefficient is, which has got viscosity, formation, volume factor, permeability in it, and then a whole bunch of stuff related to the well, and then the skin factor. And then it has to have the same contacted oil in place, and as you pointed out, the same compressibility. The likelihood of them having the same D is not very high. But, I mean, certainly, you're saying, well, if it's close, but I still would contend that adding wells together is not going to give you an exponential. It would be a fluke if that happened. It would be a coincidence. Okay? Questions about this case? So this is more of an example of what not to do, because this is a summation of wells in a field. But, in fairness, this was an example out of Arps paper, so we wanted to show it. If you were me, and you were sitting up here right now, and you could demonstrate that the summation of 3 exponentials was very close to a hyperbolic, would you spend 20 minutes demonstrating that, or would you just say the summation of, say, 3 exponentials could look like a hyperbolic?
I'll take your word for it.
You'll take my word for it? Okay, so how could you have 3 exponentials in one well? How about 3 different layers?
3 producing zones.
3 different zones. And when you add the production from those 3 zones, you get something that looks hyperbolic. And if we took this exercise and we performed it, I would leave you convinced that a hyperbolic would be 3 or more exponentials added together. Actually, if we take it to the limit, an infinite number of exponentials will be the so-called stretched exponential, which has a power law term as a time term. But if we're only looking at 3, you'd be surprised at how well a hyperbolic could match that under certain conditions. Yes?
3 different layers, meaning?
All producing in the same borehole. No, 3 different independent reservoirs. They could be 500 feet apart, or they could be 5 inches apart. But as long as they're their own independent systems,
Okay.
you add 3 exponential declines together, you're going to get something that looks, smells, and tastes like a hyperbolic. Yes, Joe?
So then you think the transient portion was the pseudo-steady state portion?
It could happen. It could happen. You just stumbled onto it. That I was giving an example of where they would all be boundary dominated flow, where they'd all be exponential. But it could be, and this was one of the experiments that was run back in the late 80s when people started doing all this multi-layer work. This could be one of the experiments that was run. One layer is low permeability, the other 2 are high permeability. And what happens is you get an extended hyperbolic because of the low permeability layer. There's all sorts of potential variations. The Kansas Huguenon, we talked about that Kansas Huguenon, do you remember that? Largest gas reservoir in the Western Hemisphere except for the gas cap now at Prudhoe Bay. Approximately 100 TCF, so pretty, it would be 1/10 the size of the Qatar Iran North Field. A lot of gas. It's in 4 different layers. The high permeability layer depleted long ago, and the low permeability layers are supporting it. They estimate that the Kansas Huguenon will continue to produce 100 to 200 years. Okay. But you've got to be careful because you could conceivably flow gas from the low permeability layers back into the high permeability layers. I'm not saying that's what happens, but you could have a condition where that happens. So this is a very pertinent observation. Okay. Next is a discussion about Fetkovich, and we spent a lot of time talking about that. So I'm going to stand up for just a second so I can gesture hypnotically and get your attention. I can't believe I said that on top of the microphone. Okay, so Fetkovich, he tried all these different things in his first paper. You saw that last night, where he came up with ideas for his own equations. He assumed PWF was equal to 0. He assumed Z was equal to 1 for the gas case. He assumed PWF was equal to 0 for the oil case, and came up with his own specialized curve. You guys like baseball? No? Yeah, a lot?
Play it.
Yeah, that's right. Okay, so these guys, they don't care about baseball, but let's try. Well, Venezuela probably does. I don't know. Do you have baseball in Thailand? A little bit?
Yeah.
Okay. So finally, I feel comfortable with this analogy. How much do you get paid if you hit the ball one time out of 10?
No, you don't even get paid.
Okay. How much do you get paid if you hit it 2 times out of 10?
You could make a case for it.
How about if you hit it 3 times out of 10?
Hall of Famer.
Sorry?
Hall of Famer.
Yeah. How about 4 times out of 10?
God. Only one guy has ever done that.
Okay. So Fetkovich, he's a pretty good baseball player, but he's still going to strike out from time to time. And his 2 models, the PWF equals 0 gas model, PWF equals 0 oil model, they never made it off the cutting room floor. They probably, looking back, he swung too hard. That was probably not the right way to go about it. Okay? And so he proposed that PWF equals 0, Z equals 1 curve, or Z equals 1 model for gas. And this guy Carter comes along, and have you guys had a fracturing class yet? No? Never? Nothing to do with fracturing? No? No? There's something called leak-off in fracturing, where the fluids leak off in its formation. There was a graduate student that wrote a paper on it, and thus changed the whole approach to how fracturing was modeled and analyzed and everything else. What was his name? Oh, yeah, it was Carter. Yeah. Okay. Where did he do it? Oh, over across the street. Yeah. So, Carter's a really bright fellow. I never met him. I would have liked to. But he worked for Amoco for probably 25, 30 years. And one of his last papers was to say, Fetkovich, I like what you're doing, but you got the problem wrong. It was the old kind of joke about the guillotine, the guillotine kept stopping before it cut people's head off, and the last guy goes, oh, I see the problem. Well, Carter said, I see the problem, and I think Fetkovich probably wanted to cut his head off. But what he was saying was that the way we were handling gas needed its own solution. So Carter sat down and he generated a slew of numerical solutions for gas, which was the right thing to do. And he showed that gas had bounds from 0.4 to 0.6 in the hyperbolic decline, but that wasn't exactly right. He also did some really good analytical work in there where he explained that since you were producing at a constant pressure, you've got a finite path, a specific path from initial pressure to to bottom pressure. It's a really clever piece of work. And you're going, well, so what? What's it used for? Nothing. But in a minute, when I show you this, it'll be obvious that where Fetkovich was advocating using the Arps hyperbolic, Carter comes in, says, here's how you ought to do it. And it was a nice, it was done nicely, and that was good. So baseball, you really don't get paid if you only hit it 2 times out of 10.
Well, now you can make the case for the home run hitters.
Yeah.
Guys will hit 200 with 40, 50 home runs and make millions.
Yeah.
And there's other guys.
So the way I used to say it is, if you hit it 1 time out of 10, you get paid $100,000 a year. If you hit it 2 times out of 10, you get paid $1 million a year. If you hit it 3 times out of 10, you get paid $25 million a year. You hit it 4 times out of 10, there isn't enough money on the planet to take care of that. So, you know, Fetkovich would have definitely been a 400 hitter, but everybody strikes out. And that was a strikeout, in my opinion. But his development of the empirical, of the analytical, that happened here at Texas A&M while he was sitting in a course like you are some 40-something years ago. And he constructed the composite, and that's where production data analysis, estimating reservoir properties was born. Okay. This is the Arps curve projected onto a dimensionless grid. In this case, the dimensionless rate is simply Q over Qi. Does everyone remember the hyperbolic equation? Dennis, do you remember it? Okay, so QDD over here is equal to Q over Qi. What is TDD? TDD is equal to DI times P. Okay? Clever, huh? I mean, you just sat down, stared at this equation, and said, I've got that variable here, and I've got that variable here. So once you make those two definitions, then you have QDD is equal to 1 plus B TDD raised to the 1 over B. So what's the only parameter on this graph? Flat. Very good. Cool, huh? So in theory and in practice, what you could do is you could overlay data onto this and estimate QI, GI, and B. How would you have solved this equation, either form, in the late 1960s? How would you do it now? Okay, what's the computer? How would you get a computer to solve that for you? Plugging in numbers. You're a mathematician, that's your vocabulary.
Recursion?
Recursion is not the right word, but you're in the right ballpark. Regression. Okay. What's the name of the product or the package that you would use for regression? You know, this is the difficulty for me and for my very dear friend, Dr. Valco, is that not all the world's great problems can be solved in Microsoft Excel. But we will try. Okay? So you have a column of time data, a column of rate data, and you have the equation in the upper right-hand corner. What can you use to solve that? Solver. Okay. Is solver perfect?
No.
What's its fault?
Doesn't use Newton rough.
It has a variety of different algorithms. Go ahead, Dennis. You're about to say something.
Is it limited to one variable that it can solve for?
No, that's scroll 6. Solver can solve for many people. It can too. You know anything about regression? You're supposed to have a mathematician, not a statistician. Neil? You ever use solver, right?
Use solver, yeah. I don't know how it works. I wish I did.
Drillers? No hot wings? Ron, have you ever used solver?
No?
Only to do your bank account?
I guess it's for estimating.
Sam, have you used solver? Who's used solver frequently? Somewhat frequently. Okay, tell me, what's the biggest problem with it?
I guess it's for estimate.
Sorry?
The first estimate that you.
Okay, the initial guess,
Yeah.
very good. You know, everybody needs to understand that all of us have personal quirks. I relate everything in life to either my children or my dogs. So I had a dog one time that was a dachshund, and like having a daughter, you know, it's not that you didn't want it, it was never something I expected. But my wife went out and bought this dachshund, and believe it or not, she stole my heart. But she would chase a tennis ball forever. And if you stopped throwing it, she would go get it and drop it by the door, and, you know, there would be a pile of them. She would want to play tennis ball. And I remember my father-in-law had to throw the tennis ball for like 4 hours one day, and he said, "There's something wrong with your dog." And I said, "No, there's something wrong with the human playing with the dog." But when I wanted to leave, I would pretend to throw the ball, and she would chase it, and I'd put it in my pocket and walk in the house. And I understand somebody's going to call the animal cruelty people, but what she would do is when she didn't see where it went, she would walk the perimeter of the fence. I would sit there and stare out the window, and then she would grid search until she found it. That's the kind of thing that Solver does. There's various algorithms in Solver. You set the space of where it can go, and then it's going to search for it. You can either go minimum or maximum, and every time you go into Solver, you better remember which one it is, because the default is maximum. I was trying to do something the other day, and I was like, why the hell is this thing solving? This is going for the maximum, not the minimum, which is really stupid. What's the deepest place on Earth? Yeah, that's one place.
Mariana Trench?
Mariana Trench. Anything else? No? What about Death Valley? 250 feet below sea level? Something like that? What about the Dead Sea? 1,300 feet below sea level? Okay. Marianas Trench, 30,000 feet? Something like that. Isn't there a place in former Yugoslavia that's 7 miles of caves? Something like that. It's not really a fair comparison, but would you find the Marianas Trench if you were looking for it in Europe?
No.
Do you guys understand now how Solver works? If you don't tell it where to look, it's not going to find the right solution. And also, what if there's a trench near Marianas Trench? Could it possibly go to that one instead? Yeah, it does it all the time. If you want to check Solver, take the numbers it gives you, apply a random factor to them, and run them again, and see if it comes back to the same place. If it doesn't, you're in trouble. I recently saw an SPE paper where somebody ran Solver to do this kind of work, to do decline curve analysis work. They did not put enough terms in the iteration. The fits did not look right. The fit did not connect to the data. And I was like, something's wrong here. And they were nice enough to explain that that was good. But you know, be very careful with automated algorithms. Okay. Everybody's okay with this part of the discussion, the empirical part? This is just the equation in the upper right-hand corner, converted to dimensionless form, and then solved graphically. Major accomplishment. Really powerful for late 60s. Yes?
So, time isn't really dimensionless, or what's the?
It is, di is 1 over t, and then t is t, so it cancels out. That was the beauty of the cleverness of it. It was so simple. Okay. All right, the next is where he then, and this is what he did here, he then, like we showed last night, he took these as so-called chatted curves, or been everything in Earth curves, and he took these curves and he overlaid them where they all drop down, where they have an exponential decline. In other words, they all have the same terminal signature. So he did that, and when he did, they all condensed like this. Okay. There's really no magic here, because he knew that this had to happen. Okay, so he's got a dimensionless time function for the analytical model here, he's got a dimensional time function for the empirical model back there. And it just so happens that by judiciously putting these two together, he generated this. And
How old is he now?
he probably would have been in his late 30s and 60s, maybe. On the order of that, he's probably 80 now. So, remember what I told you, concave up is transient, concave down is boundary dominated flow, okay? Everybody's okay with that? And so right here is where it switches. The only analytical part on this whole curve, on the right-hand side, is here. You know that because I showed you the derivation before. This is the only analytical curve, the only one that has an actual model. It's the exponential decline. Okay? All the rest are what? Then? These are all empirical. What does empirical mean, class? Based on observation. Can we derive it? Not exactly. Okay, so are they real or not? We don't know. Everybody happy with this? So this side, the whole thing is analytical. Every value. This side, this is the only analytical curve. And it kind of sort of runs along the bottom here. Well, I mean, it would be any one of these if you want. Sorry, that's really poor. Didn't mean to confuse anybody. They would come in like that. So what's left? This is all for a liquid. What about gas? Then? What Fetkovich say? Fetkovich said that all the gas curves fall between these two. And for the sake of argument, that's probably fine. Now again, for the 10,000th time, we're talking about conventional reservoirs, boundary dominated flow. We're not talking about shale wells or ultra-tight gas. We're talking about normal stuff. Okay. So if you were me, the next slide is talking about all of the explanations, and I've just covered everything that's on here. Now, what happens if B is greater than 1? And as I mentioned before, and as Fetkovich mentioned in his paper, you would take a pair of scissors, cut this out, and move it over here. That's what he was trying to explain. These are not pseudo-steady state. Okay? There cannot be a feature that causes this in nature. The only thing that can happen is if you inject enough, you could push one of these curves over. But like I told you, you're not going to see that.
So let's say if it ends up at the B equals to 2, you'll be wait long enough, it will decline two.
If the value is B equals two, okay, what did I tell you? B equals two is a slope of a half on this graph, right? I didn't draw that perfectly well, sorry. Okay, Sam? So, 1, 2, 1, that's a half slope. You agree with that?
Yeah.
Alright, so I'm gonna take this line and I'm gonna bring it over to here. Again, I moved my triangle, sorry. So that's a half slope. Where's the quarter slope, Jeffrey?
At the 4, along the side of the 4 line.
If I take this and I make a 1 to 4 line, 1, 2, 3, 4, 1, and I transfer that. So this implies 1/2 slope implies what, class?
Linear flow.
Q is proportional to 1 over square root of t, correct? 1/4 slope, Q is proportional to 1 over
What over the
the 4th root of t. Let me draw 4 there, 35, okay? Where do those belong? They belong over here and over here. When we start talking about the right reservoir model. This is not the right reservoir model, this is radiant flow. So you're not going to see 1/2 and 1/4 of the radiant flow. But Fetkovich said it, I've said it, everybody please listen. If you see a V value greater than 1, it is transient flow, and you should not be over here. It's that simple. And again, the reason I'm being so hard on this is because one day you're going to be doing reserves, and you're going to want to push the V value up as high as you can, and nobody's going to be watching, and blah, blah, blah. You know, just don't do it. For unconventionals, we have a way of handling this. Yes.
You just said that, it's possible if you inject enough, say we did inject enough, can that region be used to both, perform, to get transient properties and also volume as well?
You know, the bad thing about being me is that I got a really small brain. I try to stay focused. Wrong, sorry. Wrong. Sorry, all the graphs are at the bottom. This paper should have been published. Alright, so what we did is we created a behavior at the boundary that was either a step injection or a slow recovery. So it would either be an injection front or water influx. Okay. And so what does that look like? It looks like this. The actual decline gauge should be up right here. I'll zoom in.
not published, how come it has an SPE number?
No, SPE number doesn't mean it's published. Okay, so here what you're looking at is the original decline is here, and then there's all these recovery curves. This is a case where there's a step change at the external boundary. So bang, at certain time, influx starts, and you can see what happens, okay? So there's external energy being added at the boundary. And then there was another case that we did, it was called a ramp rate, and it looks like this. This is more of what you would expect. The ramp rate has a traditional decline, and then it rolls over into a secondary decline, okay? How many cases did we see with data that actually matched this? Since you asked, Jeffrey. Here you go. There's one. This is a water flow case. Water flow case. And then this is, trying to remember where I got this case. I can't read it. It's the La Sierra well. It's in Colombia, and you can see that it recovered. But who knows? I think it was water flood behavior. Okay.
What were the parameters you used to do that, to dimensional?
What we did was we came up with a dimensionless characterization of the ramp. So there would be a dimensionless time when the ramp started, and there would be a dimensionless impulse, like a dimensionless rate at the outer boundary. This is totally nonsensical. It's a great research problem. Should have been something that, you know, we pursued more, but nature does not do this. You know, we had a perfect laboratory to investigate this. We had something like 350 wells, and with access to another couple of hundred on a water flood. It was, at the time, it was the largest automated water flood in the continental United States. So we had excellent data on every well. We had literally daily or hourly pressures on all the injectors, and we had pretty good data on the producers. So we were pretty comfortable with what we could do here. But the goal was to demonstrate this recovery, and we had very few wells that showed this kind of recovery. I mean, you'll see a stabilization, but you're not going to see, you know, a jump back. Now, we do have that included in here, and there are a couple of cases where you see the jump, and you can see the jump here as well, that there's a recovery, there was a decline, and then a recovery. But all of these had a normal type of decline, and then a bounce recovery, whether you were looking at that one or this one. Here's the bounce. Here's the bounce. Again, I just want to say that, you know, it's a great problem or a great thing to illustrate something, but I don't think you'd want to try to use this for practical purposes. Okay. So again, anytime you see B greater than 1, external energy in the system, i.e. transient flow. That's one story. Okay, then comes Carter. And actually, believe it or not, the red lines on this curve are not numerical simulations. They're an analytical solution that Stephen and I derived. But what Carter showed is that actually the family of behavior lies below 0.6, and in fact, it's I believe it's below 0.55 on the B factor chart. But you can see that these red curves do not align with the black line. What does that mean, class? It's not hyperbolic. I'll repeat it again. It's not hyperbolic. The gas case looks, smells, and tastes hyperbolic, but the analytical solution or the numerical solution for gas, whichever one, because they're overlaid, it's not hyperbolic.
The red is another.
The red is actually a numerical / analytical solution for gas.
And the black is the
black
data.
is B equals 0.1, 0.2. It's the Arps model. The black is the empirical, and the red is the analytical gas model. Okay. So what does it tell you? In simple language, it tells you that using a hyperbolic for gas is optimistic. In simple language. Hence, Dennis, if we use a terminal exponential, what is that? Is that better than a terminal hyperbolic? Yes. Yes. So is this exponential like? Yes. Is it hyperbolic like? Sort of. So again, for the 10,000th time, I'll sleep fine at night if we utilize a hyperbolic model for part of the curve and an exponential model for the other part. It's not something I would have advocated 5 years ago, but you know, if you're going to use a tool that's out there, this is probably as good as anything else.
So what was good for gas?
Gas probably should be represented by an exponential or a near exponential, not a hyperbolic. You can see it in the red curves. They're not hyperbolic. And I know some of you are saying, but they look hyperbolic. It's on a log-log scale. And it's close enough. And I agree. But it's still going to be an overestimate. What's the key then? Always be conservative. Is everybody satisfied with this? Yes, no, maybe. All right. Now this is the 1980s, and this was sort of where we decided that we were going to try to analyze whatever data we had. This was the advent of platforms in the North Sea, and platforms in Nigeria, and platforms in Indonesia. And why am I mentioning these places? Platforms in Thailand. How many platforms are there in the United States? In the Gulf of Mexico? Any guess? 1,000? Something like 4,400, 4,500, maybe a few more or less. Is that a lot? That's a lot. And they all magically end at the Alabama demarcation line. Has there been oil discovered in the Florida area? Yep. Has there been gas discovered? Yep. How come we can't drill there? Yeah.
The marine line?
How many offshore platforms are there in California? Maybe a dozen. I mean really offshore, not the wharf. But how many more will be built? None. In fact, when I was doing a project out there in the very early 90s, they had invented extended reach drilling. You know what extended reach drilling is, gentlemen? That was 20,000 feet. You know, they were reaching out 20,000 feet because they weren't going to be allowed to put another platform out. You want to know where several billion barrels of oil are? I can tell you. Just beyond, you know, your ability to get to it.
Was it Oxy?
Hmm?
Was it Oxy?
This was, at the time it was Unical, and it's, you're thinking about the island, in Long Beach, but I'm thinking about Platform Gila, Platform Grace, which was the Chevron platform. And then, Unical had the Dos Padres sequence of platforms over offshore Santa Barbara. And they had to have an act of God to get permission to drill multilateral wells off of those Padres platforms. Everybody realizes how shallow the oil zone is there. It's at 800 feet below the sea level, below the mud line. They had a blowout there in 1968. It almost ruined the oil industry in California. They had to be extremely careful with, they were drilling triple multilaterals in this formation. Great, there's plenty of oil there, but, you know, all the folks are gathered on the, do you know why you can't close the refineries? Does refinery demand warrant more or less refinery capacity? Probably now that'd be true, but 5 years ago. Sam, how come you can't close a refinery? Can't afford to. First thing they do is they come out and they cut a core 100 feet down. They find hydrocarbons. Who pays to clean it up? Try decommissioning a refinery. Try decommissioning a fuel facility. It's going to be tough. So at any rate, we got all this data coming in because these guys are taking bottom hole pressures. I mean, it was a fantastic time. Offshore California, they had a bottom hole pressure device. It was a capillary tube, but the pressures were fine. It was a very small stainless steel tube that they flush out with nitrogen every few days. And what it would tell you is the surface pressure, and then you calculate the column of nitrogen, and it would give you the bottom hole pressure. Excellent. They also had ESP with pressure sensors on it, electric submersible pump. So they have an intake pressure device on it. So really good pressures there as well. So when you're taking all this data, you got to do something with it, right? Now you have people with all these downhole gauges, and they're trying to figure out what to do with the data. This guy, Achikchangakorn, can you say that for us?
What?
Achikchangakorn.
I should not go.
Yeah, see, even you have trouble with it. The name that's missing there, the et al. Is Horn out of Stanford. He's still working on permanent downhole gauge problems. And I said superposition is impossible. What's impossible mean? You had petty 6-1, right? So when we start making calculations where we take a step out, that's the first step. We have 1,000 steps, and how many steps do we have to take? 1,000. When you have 1 million, how many steps do you have to take? 1 million. And each step, you have to go all the way back to the origin and start over. How are you going to process 1 million data points? You're not. Okay. There are some tricks. You can take the data on the Blossom man, but then what happens? You got to get out. And by the way, the same steppy thing you got to do to get out, so it's not going to work. There's really no way to speed this up or slow this down, but maybe there's a way of overcoming a few things. Then we talked about how to define rate normalization, which was really where I came along, material balance time. Then we had examples, and then later on we started talking about how to do type curve matching with variable rate analysis, and that was analogous to what Fetkovich was doing with some auxiliary functions. Material balance time makes everything think it's constant rate, which is great. It's a zero-order deconvolution, so it allows you to solve an equivalent constant rate problem, so it's much more straightforward. Okay. Got about 10 minutes left, and I'll cover this quickly. So again, how many steps do you take here, Tim? You got 1,000 points, you got to take 1,000 steps, and if you look at this calculation, you've got to go back to the origin every time. So this gets better or worse the more steps you have? Worse. So the speed will decay, maybe not exponentially, but it will decay, probably geometrically. Okay. And there's a rate equation and there's a pressure equation, and these are exact. They're straight from the theory, provided you have exact inputs, provided it's a liquid, blah, blah, blah. Okay. So my buddy with Kappa, he decides, well, we'll just solve this all numerically. But then you lose your diagnostics. Yeah, go ahead.
So is it limited by the data?
In theory, but there are some tricks you can use to speed it up. But whenever you run one of these, if you ever get into this sort of thing, you never want to run the nonlinear solution. It could take days, because it will not only have to run the calculation, it'll have to check each step to make sure it converged in terms of pressure. And the vendors have been very careful to try to balance speed and accuracy. But every now and then you'll run one and it just will look like crap, and it's because you exceeded it, whatever trick they're using to speed it up. It happens, you know. But suffice it to say, this is not the grand challenge problem. You know, at least we know we can do it. Given time, given the algorithms we have, it'll run. But again, this is exact. For exact inputs, you get exact outputs. And this is what was attempted by Van Everdeen and Meyer in the late 1960s. They created a superposition function using the top equation, and they showed how to use it. But nobody wants to look at a superposition function. What do you want to look at? You want to look at data on this plot, and then a line going through the data, which is the model, right? You're trained to look at that. Your brain is wanting to see a comparison like that. So that's what these equations will do for you, is if you have data, you take the rate to calculate the pressures. If you have pressures, they calculate the rate. And of course, all of that assumes that you know what, Sam? You know the reservoir properties, you know the reservoir model. Okay? So you must know permeability, skin, fracture half length, all the other things. Permeability and formation volume factor and thickness and viscosity that I circled on the left-hand side, those are just scaling things. The real meat is inside the model, the PSC and the QD.
What does that?
Those are the dimensionless solutions. One is for the constant rate solution, the PSV. Okay, so very quickly, again, the people out in the real world are going to get to the point. So let's get to the point for them. All right, so PSV. Dennis, give me some options on PSV. We can have a well and an infinite reservoir. We can have a well and a circular reservoir. We can have a fractured well and an infinite reservoir. We can have a fractured well and a circular reservoir. We can have a horizontal well and an infinite reservoir. We can have a horizontal well and a rectangular reservoir, et cetera, et cetera. All of those come back to this. Okay? It's our mathematical nomenclature. The PSD is the dimensionless function that represents the model. So if you want to think about it, this is the engine, okay? So you could have, like I was saying, you could have engine number 1, 2, 3, 4, 5, 6, you know, there's literally nearly, I wouldn't say infinite, but there are just hundreds of combinations that you could have. You could then have finite conductivity fractures. You could have fractures coming into the horizontal well. You can have a well that's tilted. You can have a well that's slant. You can have partial penetration. You can have various types of skin. You can have a heterogeneous reservoir solution of one type. You can have a heterogeneous reservoir solution of another type. You can have a composite region where there's an inner region and an outer region. You can have an elliptical flow model. You can have all sorts of different things. Just about anything you can imagine somebody's created a model for. And all of those fall into the category of that PSD. So in software vendor K software, you go to the menu, you first pick the reservoir, or sorry, the well type model, then the reservoir type model, and then the boundary type model. And so you can see this near infinite configuration. They all go back and they calculate PSD. In vendor F, it's something similar to that. You punch on there, up pops the model, and you populate it however you want. But perhaps vendor K is a little bit more easy to understand because it's a multi-step menu. First you pick the well, then you pick the reservoir, then you pick the boundary.
So it's just a general description of what your reservoir is?
And then vendor K has a numerical model that's sitting out there, and you can configure it any way you want. And it's sitting, you have a button for analytical and a button for numerical, and you just push the button you want, and off the model runs. And again, for the 10,000th time, this is just a tool. There's no analysis here, there's nothing else. It's ugly, it's brutal, but it's just a tool. Once you get the model set up, you give it the properties, you give it the times, the rates, the pressures, and they generate them. That's how this works. If you want tonight, I can give you a quick demonstration of this, but I don't want to spend a lot of time on it because it's just going to confuse people.
But the same thing when you did the simulation where you try to.
That's exactly what it is. That's exactly what it is. And you can just jump from one thing to another and change it however you would like. But, if you don't use geologic guidance when you're performing analysis, you cannot apply a fractured well to an unfractured well, can you? Well, technically, yeah. You cannot apply a horizontal well to a fractured well, can you? Well, believe it or not, they have the same basis. They're different geometries, different this and different that. But you see where I'm going with this. Oh, by the way, you can also make all of these multi-layer. They can accept, you know, it'd be like having a well in one layer, well in another layer, well in another layer. You can tie them all
The
together.
way you present it, it sounds like this whole thing's nonsense.
Non-unique.
No, he meant nonsense,
I mean,
because it's too much. His frequency of assimilation is much lower than my frequency of blurbing it out. So, what he has to understand is that this is not part of this course. Whenever you start to work in reservoir performance, you build this systematically. You start at the simplest point and you work your way up. This is one of the reasons I don't like teaching software, because the second you teach software, people jump to the most complicated configuration. They have no idea what, I guarantee you that if you go and ask the people who've taken the graduate and the undergraduate courses in well testing in this department, they're not going to know that those two equations are the engines behind the software. They're not going to know. Now, we derive those in 620. And the reason that we derive them is because I don't want you to abuse them. You know, a lot of people tell me you don't have to be able to build a car to drive one, but you damn sure respect it a lot more when you do. And my colleague, Dr. Merides, who's really into numerical modeling, you know, his course is brutal. Not a lot of people, you know, are going to stand in line to take it, but when you come out of there, you're never going to be afraid of numerical modeling again. You're never going to be afraid of analytical modeling again when you're done with me. Dr. Valco, his course on Mathematica, Dr. Gilding, his course on setting up reservoir simulation, you know, those are the kinds of foundational things that really, you pick up all this. But for the purpose of 663, no. I mean, the purpose of 663 is when you're a manager 25 years from now, and somebody tells you they want to run a build-up test, you at least understand why they're wanting to do this. You know, the first question out of your mouth as a manager is going to be, how am I going to get my production back? You know, that's unfortunate but true. So what's the next question? As a young engineer, it doesn't matter, sir. What we need to do is understand the nature of the reservoir so that we can make better wells. And, you know, every day, I did a webinar last week. Every day I've gotten an email asking me to speak somewhere else, asking me to give more information. There's so much of a lack of fundamental understanding out there. And these were people who were competent asking me questions. But there's so much of a lack of understanding out there about certain things that once you start having information overload, you make bad decisions. So, anyway. 7 o'clock tonight?
Maybe we can do a problem on fitting data on an Arps.
We can do that. You really want to? I'll do it for you. I've got a demo that'll work for you. Anything else tonight? Yes, sir.
You modified the second lecture. Are we responsible for the stuff that you don't have in it?
Like,
Well, there's 278 slides for production.
no. Well, you're responsible in the sense that you'll have it in your lap when you're taking the exam. And let's say that I ask you a combination of true, false, and problem. If I say you can determine reservoir properties without using transient flow, although I have to be more specific than that. You can determine permeability from pseudo-steady state flow. If I ask you that, what's your answer? It's an absolute, it's false. But did we cover that exactly in the notes? No. Do we cover that in class? Yes. Are you responsible? Yes. There could be an inverse of that as well. So that's fair, I think. I mean, you're gonna have the notes in your lap, so it's okay. My goal is not to see you flipping through pages. My goal is to establish the foundational knowledge that you're able to answer questions. Okay, so don't let me forget about that. I can pull it if I need to. I'll stay long. All right, everybody, thank you. Including you, Hefe.
Can I close this?
Yeah, go ahead. Sorry.
I have a question.
Huh?
To visit that?
No, that'll be a window. You'll check it out over a 3-day period, you'll have 3 hours. I'll let Ted handle all that.
So it's gonna make this call or something?
I don't know, whenever you want. When you check it out, he'll send you an email with that.
No, I know that part, but when would be like the last day you can get in and do stuff? 14 as well?
Probably what'll have to happen is I'll have to put some sort of deadline
Yeah.
where I stop accepting. Well, if it's all graded mechanically, I could probably go to the 15th, except for the people who are graduating.
I don't think you because I'm moving.
Yeah,
So
let me visit with Ted and make sure. The weak link here is that the grade book is not in my possession. Okay, the grade book. There's 3 instructors.
Yeah.
I'm
So,
just
yeah,
one piece,
yeah.
you know. I need to talk to Ted and make sure that once the grades are entered in here, that Dr. Ayers can pull
The whole
the district